tabla și toate astea. Eu. Păi, ce am nevoie de asta? Okay, you see the table, yes?
Yes.
Okay. So now let's talk first about partial derivatives. So partial derivatives are about functions of several variables. Functions of 2 variables, 3 variables, these are the usual examples. For example, f of x and y equals x squared plus y squared times e at minus x squared y. This is a function of 2 variables, x and y. And so on, a function of 3 variables, f of x, y, and z. It's, let's say, xy plus z squared times e at minus x squared plus yz, and so on. Yes, functions of 2 and 3 variables. Now, first, computing. A mai intrat cineva? Nu. Okay, so now the first subject here is to compute partial derivatives. Now, about the definition, the theoretical definition, we have everything in the lecture. So, to compute the partial derivatives, if I remember right, not Monday, but last week at the Rose class, with those students which are present here, we discussed about partial derivatives. You were among them?
Yes.
Yes. So then, do you want to repeat this or want to continue to go further?
Can continue.
With partial derivatives. Then, okay. Let's compute the partial derivatives of this function. And then we shall move forward. The Rondev to the Rondex. What it means to compute the partial derivative with respect to x. It means that x is the unique variable, yes, and y it's a constant. In that moment, we shall use the rules to compute derivatives for functions of one single variable, which is the variable x in this case. So let's differentiate here with respect to x. Y, it's a constant. So it will be 2x times e at minus x squared y. It's a product, yes? We apply the usual rule for the product. Plus x squared plus y squared not derivated times the derivative with respect to x of the exponential, which is e at minus x squared y, times the derivative with respect to x minus 2xy. Very well. Now, usually we try to, we finish the differentiation. Now, as usual, when we compute derivatives, we put them in the simplest form as possible because we shall need to work with them. So in this case, at least we can take a common factor here, 2x e at minus x squared y times what? This is 1, and this is minus y times x squared plus y squared. Okay, so this is the partial derivative with respect to x. Let's see, the partial derivative with respect to y of the same function. Again, it's 2y e at minus x squared y plus x squared plus y squared times the exponential. Now with respect to x, it will be e at minus x squared y times what? The derivative minus x squared. Very well. So again, here we take a common factor, which is the exponential, times 2y minus x squared times x squared plus y squared. Okay. This is the partial derivative, the derivative with respect to y. Okay. Similarly, for a function of 3 variables, let's compute one variable. For example, let's compute for this function the partial derivative with respect to, let's say, y. There on f to there on y. It will be here. It will be x times e at minus x squared plus yz plus xy plus z squared times the exponential now. E at minus x squared plus yz times what? If we differentiate with respect to y.
Times z.
Times z. Okay, and further we can compute. Okay. So if you have any question about computing partial derivatives, please, or maybe if you have an example or an exercise that you think is more difficult, please tell me and we shall try to solve it. Okay, if not, let's continue with higher order partial derivatives. So if we have a function of 2 variables, it has 2 partial derivatives, there on f to there on x, and there on f to there on y. Now, these are functions exactly like f. These are functions, both of them, of 2 variables. That means that they both have partial derivatives with respect to x and with respect to y. We can differentiate with respect to x the function there on f to there on x, and the same function with respect to y. We shall write like this. There on to there on x means that what will follow, we must differentiate with respect to x. Same story here, there on over there on y, of there on f to there on x. That means we shall differentiate with respect to y the function there on f to there on x. Similarly, there on f to there on y has a partial derivative with respect to x and a partial derivative with respect to y. Yes. Now there are some specific notations. This one is denoted as there on 2f over there on x squared. It means that we shall differentiate 2 times the function f with respect to the variable x each time. This is denoted by there on f, there on 2f over there on y, there on x, and it means that we shall differentiate 2 times the function f as follows. First, with respect to the variable x, and then the result with respect to the variable y. Here, this one, it means we shall differentiate f 2 times. First, with respect to y, and then the result with respect to x. And here we differentiate 2 times f, each time with respect to the variable y. Attention to the specific notations, especially to this, which are, these are called the non-mixed second order partial derivatives. It is, the name is very clear, y second order, while these one are the mixed, because the variable are mixing. Mixed second order partial derivatives. Okay, and a question, if I think we discussed last week, was about the mixed partial, the second order partial, if the order of differentiation matters. So are these two equal or not?
Most of the time.
Most of the time, okay. Yes, most of the time means when this second order partial derivatives, all of them are continuous. Yes, if all these 4 functions written here are continuous, then yes, these two are equal. Okay. So this is called the symmetry, Schwarz symmetry theorem. So we shall work always with functions of at least class 2. So these functions are continuous. So the relation, this relation will be always true. we can use it. So that means that for a function of two variables, the second order partial derivatives, we need to compute only 3 of them because these are equal. Or in other terms, the order of differentiation doesn't matter. Okay, very well. And now, you told me that you want to discuss about Taylor polynomials. Yes, let's discuss about Taylor polynomials. Okay, so Taylor polynomials. For attention, for functions of several variables. Okay, now Taylor polynomials for functions of one single variable was like this. For instance, if f is a function of one single variable, the Taylor polynomial of the first degree at some point a, yes, was like this. It's f of a plus f prime of a over 1 factorial times x minus a, while the second order Taylor polynomial is f of a plus f prime of a over 1 factorial times x minus a. And until here we have t1. Yeah? And then we have another term of second degree, f second of a over 2 factorial times x minus a squared. Well, now for a function, let's write for two variables, f of x and y. The point will be AB. Yes? Instead of A, we have AB. Now, we shall see at the lecture what is the idea behind. But it's very simple. If we inspire from the theory of functions of one single variable, then the Taylor polynomial here will use the partial derivatives, first order partial derivative and the second order partial derivative. So T1 of x and y will be given by f of a and b, the value of f at that point, plus. And here we shall have 1 over 1 factorial, like here, times. But this time, here we have two partial derivatives, first order. So it will be der on def to der on x at the point A, at the point AB, sorry. This is a function of two variables. Times x minus a plus der on def to der on y at the point AB times y minus b. This is the first degree, or it is also called the linear approximation of f around to the point AB. The properties of this Taylor polynomial are very clear. Its value at AB equals f of AB, because if we put here x equals a and y equals b, these two terms will be 0. So you get this one. Also, if we compute the partial derivatives with respect to x and with respect to y of this polynomial, we shall see that they are constant, der on def to der on x at AB, because if you differentiate here with respect to x, you'll get only this number. The same for of y. So the Taylor polynomial the first order has the following properties. It is equal to the function f at the point AB, and its partial derivatives. Remember the ideas for Taylor polynomials of one single variable, yes? Okay. Very well. Now, while the second order, we'll add here some second order partial derivatives, but attention. So first of all, we have the linear approximation. And now until here is T1 plus. And now we shall have the terms of second degree. Now here the second order partial derivatives will be used as follows. Maybe you inspire from this form. It's 1 over 2 factorial times. How many second order partial derivatives do we have? 4, yes? Thereon 2f over thereon x squared at the point AB times x minus a squared. Now plus. Now we have the mixed. But the mixed are 2, but they are equal. So we shall have 2 times thereon 2f over thereon x thereon y at the point AB times x minus a times y minus b. And finally, thereon 2f over thereon y squared at the point AB times y minus b squared. This is the quadratic approximation of the function f around the point AB. Okay, now, of course, the use of these polynomials in 2 variables is to approximate the values of the function f close to the point AB. Okay, let's see some application. Let's consider the function. Let's consider the function f of x and y equal, let's say, x squared plus y times square root of let's say y. Okay. At the point AB, let's take it to be 1, 1. Okay, so the linear and the quadratic approximations of this function at the point 1, 1. So, okay, let's put it minus 1, 1 to be less symmetric. Okay, now the formula is here for the first order and for the second order. What we need? Well, we need to compute the value of f at the given point, 1 minus 1, 1. So in first, f of minus 1, 1. That equals 2, 2. What? Now we need a partial derivative, for derivatives at the point AB. Of course, we shall compute them by using the rules for differentiation, and then we shall apply at that point. So first of all, thereon def to thereon dex at some arbitrary point. Let's compute it. It's 2x times square root of y. Yes. Plus x squared plus y. The derivative of this one with respect to x is
0.
0. So actually this is a constant. It goes in front of the differentiation and we get this. So it's 2x square root of y. And thereon def to thereon y at some arbitrary point. Now this time we don't have a constant. That will be square root of y plus x squared plus y times 1 over 2 root of y. Okay. And now we need to compute this. Let's put them in the simplest form because we shall need to compute the second order, so we shall continue. How to handle here? I think we shall leave them as they are. And now let's compute them at the given point, minus 1, 1. The first one will be 2. Sorry, no, it's minus 2. x equals -1, so there will be -2. And there on f2, there on the y at -1, 1. It is this one. We shall put here, that would be 1 plus 2 over 2. That means 2. And now we can write the linear approximation of f. The Taylor polynomial of first degree. That will be, the formula is written here, yes? T1, that means f of fb, we have, all we needed are written here. So it's 2 plus 1 over 1 factorial, that is 1 of course, but we write it to have a complete formula, times the partial derivative, this one it's -2, times x plus 1, yes? Attention. X minus, say, y minus b, this vector is, in our case, x plus 1, y minus 1, yes? So it's -2 times x minus 1 plus 2 times y minus 1. Okay, this is it. This is the linear approximation of f. We can write it, for example, 2 plus minus 2x minus 2 plus 2y minus 2, which means minus 2x plus 2y minus 2. This is the linear approximation of the function f written here around the point -1, 1. So if somebody wants to compute approximatively, for example, f of -1 point, comma 1.01, we can use this formula to approximate, because this point is close to this one. Or we can also here change, instead of -1, we can put -0.9, for example. So approximate the value of f at -0.9, comma 1.01 by using this Taylor polynomial. Now the second order Taylor polynomial. For that, we need to compute the second order partial derivatives. Attention, the first order are written here. So now there on to f over there on the x squared will be 2 square root of y. There on to f over there on the y squared. Let's start with the not mixed. We need to differentiate here with respect to y. That is 1 over 2y, 2 square root of y, plus 1 over 2 square root of y. We differentiate as a product, plus x squared plus y times, now the derivative of 1 over square root of y. You can differentiate it as a power. It is y at -1 over 2, differentiate it. It is -1 over 2 times y at -3 over 2. Yes, the derivative of y at -1 over 2. It is this one. Okay, we can get here, we have 1 over square root of y, these two, plus x squared plus y minus. Over what? Over 4 root of order 3, root of order 2 of y at 3. Or if you want to write it, y square root of y. This is the second order. These are the two second order partial derivatives, not mixed. And now the mixed one, we need to compute only one because of the symmetry theorem. We can do it in two ways. There on 2f over there on x, there on y. We can differentiate here with respect to x, or we can differentiate, or we can differentiate here with respect to y. Let's differentiate with respect to y, the first one. It seems to be simpler. So it's 2x times 1 over 2 root of y. We simplify and we get x over root of y. We have all the second order partial derivatives we need. Okay, we need to compute them at our point, but that is simple. So the second order partial derivative of xy will be the first order, this one, minus 2x plus 2y minus 2, plus 1 over 2 factorial, which is 1 over 2, times the partial derivative with respect to the second order partial derivative with respect to x, which is this one. At our point, don't forget our point is minus 1, 1, yes? That is 2. Times what? Times x plus 1 squared. Yes, I use this formula. Plus 2 times, now the mixed one, which is this one. At minus 1, 1, that is means minus 2 times minus 1, that is minus 2. Yes. Times what? X plus 1 times y minus 1. Yes, like here. And now plus this one. At the point minus 1, 1. That means 1 negative. Here it's 2 over 4 times y minus 1 squared. So we have minus 2x plus 2y minus 2 plus 1 over 2 times 2 times x plus 1 squared minus 2x plus 1 times y minus 1. And here we get what? 1 minus 1 over 2, that is 1 over 2 times y minus 1 squared. And this is it. Okay, we can continue the computation, and this is the second order, second order polynomial, the quadratic approximation of f. Okay, so now there are some, we shall have at the lecture some explanations about how this formula are inspired, but also the inspiration from functions of one single variable are rather good. However, we shall go deeply in, we shall discuss about the differentials, so there are connections with other subjects. But for the moment, we must know them. And the idea is that they approximate the function f around the point AB. Of course, we can write something similar in three variables. At the point ABC. Sorry. How they look like? It will be f of ABC plus 1 over 1 factorial there on f to there on x at ABC times x minus a plus there on f to there on y at ABC times y minus b plus there on f to there on z at ABC times z minus c. And T2 of xyz will be T1 plus now the second order terms, 1 over 2 factorial times. Now let's see how many terms we shall have here. So then we have, first of all, the not mixed terms. There on 2 to there on the x squared at ABC times x minus a squared. Also not mixed, there on 2f there on, over there on y squared at ABC times y minus b squared plus the last not mixed with respect to z, z minus c squared. And now plus, we have the mixed, but those are 2 times because of the symmetry theorem, yes? So we have 2 there on 2f over there on x, there on y at ABC times what? X minus a times y minus b plus 2 there on 2f over there on x, there on z at ABC times what? X minus a, z minus c. And the last one, 2 there on 2f over there on y, there on z at ABC times y minus b, z minus c. Okay, this is how it looks like in 3 variables. Yes. Why here we have 2 times? Simply because there is a partial derivative there on 2f of there on x, there on y, but it is also another one there on 2f of there on y, there on x, and which are equal. So there will be 2 times, and the multiplication here x minus 8 times y minus b are anyway it's commutative. So there are 2 equal terms, and so on for the other. Because here we need to write all the second order partial derivatives, but all the time 2 of them are equal, yes? And that's why you have 2 times. Okay. So we know the formula, we replace, and we get the approximations. Now the approximations will be useful because starting from here we shall get the extrema, but I would not enter now in extrema. Next week to have the theory, yes? Okay, if you have any question related to these subjects. So Taylor partial derivatives and Taylor polynomials. Yes. Please.
Because non-mixed second order partial derivatives are in some terms if we were higher, the structure would be down of raising the sum of the first order derivatives at power 3.
Please tell me in Romanian. I didn't get it.
Vreau să zic că dacă am merge la T3, avem derivate mixte, am avea o formă similară ca atunci când ridicăm derivatele la puterea a treia?
Da, înțeleg. Da, este un fel de binomul Newton. Formal e ca un fel de binomul lui Newton. Formalismul. Dar e doar apar niște coeficienți care sunt combinări, într-adevăr. Look, if you go, let's consider this. I understand. We shall not use higher order Taylor polynomials because we don't need. But, however, they can be written? For example, let's take a function of 2 variables, f of x, y. So it has 2 first order partial derivatives, 4 actually second order, yes, and they all appear in the Taylor polynomials up to the 2nd degree, yes, they all appear, but this is 2 times because they are equal. And now let's continue. The third order partial derivatives. We differentiate this one with respect to x, and we can differentiate this one with respect to y. It's like this. This one will give us other third order partial derivatives with respect to x. And attention, the order doesn't matter, so we can write it like this. Actually, it is initially it is like that. Yes, but because the order doesn't matter, it equals this one. Yes, I mean this one. And now we differentiate with respect to y. We shall have something like this. For this one, we have another two. Yes. But somehow they already appeared. Yes. But it's important because in the Taylor polynomial they will appear all of them. For example, how many times we will have this one? Here one, here another time, and here another time. So in the parenthesis there will be 3 terms. The coefficient of this partial derivative will be 3. There will be 3 times this one at the point AB. Yes, it will appear like 3, which is the binomial coefficient of 3 elements by 1. Yes, combinări de 3 luate câte 1. De aici vine. De-aia ziceam că are legătură cu binomul Newton, dar formal doar așa. Cu cine se va mulți asta? Păi se va mulți cu x minus a la pătrat, că ăsta e de 2 ori, pe lângă y minus b. Deci acolo, în suma termenilor de ordinul 3, care va avea în față 1 pe 3 factorial, vor fi termeni de acest fel. De exemplu. Ok. But we shall not use higher order partial Taylor polynomials than the quadratic one. Okay, other questions related to these subjects? Now, related to the partial derivatives, please write the derivative. Let's learn about another useful fact. Remember when we defined the partial derivatives, we started with the following discussion. We said, look, for a function of 2 variables around the point AB, yes, we would like to know what is the variation of f when the argument xy is moving around the point AB. More precisely, we are here, we move in this direction, and we would like to know the behavior of the function. How quickly it changing its values. This is the idea. Now, and we decided to do like this. To understand what happens if the argument xy is moving like that and like that. Yes, this was the idea of the partial derivative. So, and we discovered that the numbers there on f to there on x at the point AB and the number there on f to there on y at AB, these two numbers explain us the behavior of the function if the argument xy is moving like this one, and like that, this one. But what if, for example, the argument xy around the point A is moving on this direction? Not horizontal, not vertical. Here we have, and we shall define now. I didn't do it at the lecture, but I can explain you, it's useful. The derivative with respect of f, of the function f, with respect to a given direction. Now, what it means, a direction? It means a vector. Yes, a direction like this is given by a vector. So in the plane, we shall consider S the vector S1, S2. Usually it is a verse, or it is a unit vector. Yes, this one. Yes, this is the vector S. It defines a direction, this one, and with an orientation in that, with that orientation. So, and we shall ask that the norm of S to be 1. These are, this is the usual way we define direction in the plane. For example, if I take the first element of the canonical basis, which is 1, 0, this is an example of a unit vector which defines a direction. What direction? This one. Yes. The second vector from the canonical basis is 0, it is 1. It defines this direction. These are unit vectors. The length is 1, defining. Yes. It is okay. For example, if I take minus 1, the vector minus 1, 0, it is this one. It defines this direction. Yes. Okay. And now the idea of the behavior of the function f when the argument xy is moving in an arbitrary direction like this, given by a vector, is to use the to see the to look to the projections on these directions. So we denote by der on def to der on des at the point AB, and we call, and the name is this one, the derivative of f with respect to the to a given direction S at the point AB. Is that it is actually the projection of the vector der on def to der on dex at the point AB, which is called the gradient, but this is called the gradient of f, and the vector S of coordinates S, which means the projection of this one on the direction S. So that means it is denoted like this, and it is S1 times der on def to der on dex at the point AB plus S2 der on def with respect to der on y at the point AB. Yes, this is the derivative of f with respect to a given direction S, given by a unit vector. Nothing but the projection of this vector on this direction. Yes. So this number, it's a number, yes, is a measure of how quickly the values of f are changing when the argument is moving in this direction. And now we can ask the following very important problem. We are with f at the point AB. And we would like to see what is the largest variation, in what direction. Yes, we can go in many directions. In what direction, if we are moving, we obtain the greatest variation of f. I mean, the values of f are changing very fast. This question is important for the following idea. Imagine that we have a function on a domain, yes, and we are at some point AB. And we would like to know in what points in the domain f takes its extreme values, minimum values, greatest, maximum values, yes? We are here. How to look to these points, how to find them? And one possible solution is the following. Start from here and go to that in the direction where you have the greatest variation, because in this way you'll at some moment arrive at some point where the value is the greatest or the least. So in what direction must go in order to find the minimum, the extreme values? This is of the function. This is the question we try to answer. And the answer is the following. Well, the direction S that you are looking for must somehow maximize this expression, which is the inner product between the vector S1, S2 times the vector der on F to der on X at AB and der on F to der on Y at AB. Yes? An inner product. When is it maximum in module? So if you have two vectors, the projection of one on the other, so when is it maximum? How to choose this direction? How to choose S1 and S2? Yes. For the moment, don't care about the length to be the length one, because the length one is obtained by dividing by the length of the vector, is not a problem. How to choose S1 and S2 in order to find here this expression to be maximal in module, plus and or minus, but maximum variation, increasing or decreasing, but maximum variation. The answer is very simple. Think to the inner product. When the inner product is minimum in module, when the two vectors are orthogonal, yes, then is the minimum with that, and maximum when they are collinear, of course. So S1 and the S1 must be der on F to der on X at AB, more precisely. So S must be exactly this one. Yes. This vector is called the gradient, as you know, of F at the point AB. I think I told at the lecture that is the name of the gradient. So, of course, divide by its norm, of course, because S must be of length 1. But also you can take it with plus and minus. This is the maximum. So the variation der on F to der on this at the point B is maximum with plus or with minus if S is the gradient of F at that point. And in that case, the variation will be plus or minus the norm of the gradient, which is square root of der on F to der on X at the point AB squared plus der on F to der on Y at the point AB squared. Okay, so a function has the greatest variation of its values if you go in the direction of the gradient plus or minus at that point. Yes, this is the gradient of F, this is minus gradient of F. If you go like that, the values will increase very fast. like this, they will decrease very fast. That's the idea. And in this way, we have a chance to find at some moment the greatest or the least values of the function f. Okay, this is a basic method you will see in approximation theory, optimization theory, the gradient methods. So, okay, so but remember, this is important, the derivative of a function with respect to an arbitrary direction. It is nothing but the inner product between the gradient and that direction. That direction means a vector of length 1. Okay, other questions. Now, tomorrow we shall have the lecture. We shall go further. We shall discuss about the differential, the Jacobian matrix, the second differential. We shall see how, if we have enough times to. And then next week we shall discuss extrema. But for the moment, these are the basic facts. The partial derivatives and Taylor polynomials. If you have some, I would not go to, so extrema, there will be at the lecture and we shall have a lot of examples there. Also here, next week, we can discuss about extrema because most of the things will be discussed tomorrow at the lecture. Tell me, in linear algebra, what do you, where are you now? What was the last subject? Yes,
Eigenvalues and
well, but what, for example, the diagonalization theorem, you did it.
Yes.
Okay. And now applications to quadratic forms. So about quadratic forms, did you learn something?
We did it last time on the seminar.
So quadratic forms. To recognize if they are positive, negative, yes? This kind of the sign of a quadratic form.
Yes.
Okay, we shall use them when we'll learn about extrema. So that's why we cannot go very fast with them because there are some facts from linear algebra that we need. And now it's very well because we shall use them in the following lessons. So the sign of a quadratic form, that is important for us. How can we recognize the sign? And you know how to do it with the eigenvalues of an appropriate symmetric matrix, which can be associated to the quadratic form. We shall need all these facts. Okay. So we meet tomorrow, and we shall progress with the study of functions of several variables. But for the moment, this is what you need to know. If there are other questions, actually. Okay, if not, we stop here, and tomorrow we shall go further with the theory. Okay, thank you and goodbye.